All right. Hey, good morning, good afternoon. Today we are working on section 6.12, improper integrals. We will find integrals with an infinite limit of integration, interpret an improper integral geometrically, and integrate functions over a and b that are not defined at an endpoint. So we got a couple things going on here. There are two main types of improper integrals. And the first one, and I'll come over here to the side before we jump right in. The first one, there we go, is where one or both limits or your boundaries of integration, that's not going to work, is it? Let's try again. Where your limits of integration, one or both of them could be infinity. So we could go from negative infinity to 6 of, I don't know, x squared dx, something like that. That's one type. And then the other type is if I integrate between 0 and, let's not do 0. Let's do negative 2 to 2 of 1 over x dx. And I know when you look at that, okay, 1 over x, we know the antiderivative is natural log, no big deal. But don't forget what it actually looks like. 1 over x is that curve that's in the first and the third quadrant. And we are finding the area between negative 2 and positive 2. So over here's negative 2, over here's positive 2. So all of this and all of this. The issue is right here at that y-axis that we go up to positive infinity and down to negative infinity. So what goes on there? Do we have an area? Do we not have an area? So that is another type of improper integral. We'll get into that in a second. So let's come over here to our notes. Recall that fundamental theorem of calculus. We have the derivative of an integral from a to x of f of t dt is equal to f of x. That's the one where we just replace the t's with the x's. We got pretty good at those. And then the second one is we have the integral from a to b of f of x dx is capital F of b minus capital F of a. Those are the two antiderivatives. So this is the version that we're focusing on today. But again, what happens if a or b is infinity or negative infinity? Those are your improper integrals. So the table below has those different types in there for you. If we go from a to b, or excuse me, a to infinity, negative infinity to b, or negative infinity to positive infinity. And what happens is we know anytime that we have infinity, infinity is not a real number, it's an idea. So we have to introduce that limit. And that's not new to us. I mean, we talked about that in our first unit together. I have a couple examples for you. If we have the integral from 0 to infinity of 4e to the negative 2x dx, and that's equal to the limit. So we just rewrite it as a limit problem. We find the antiderivative, put the values in, take the limit as b goes to infinity. We'll see what happens there. Same thing with the other one, infinity in the upper limit. We find the limit as b goes to infinity, and we put in the values. Now, I have two new words for you. And these will get used a whole lot later on, but the first one is converges, and the second one is diverges. So they're pretty easy, it's just different notation. You just might want to jot this down over here. Converges means that you have an answer that's a number. You have a numerical answer. It could be positive, it could be negative, it could be a whole number, it could be 0, but it's an actual number. Diverges, we say for positive infinity and negative infinity. So I know in that first unit with limits, we would say, okay, the answer is infinity or the answer is negative infinity or it does not exist. But now we're going to say that it diverges. It goes on forever and ever and ever and ever. So that's just some new notation for us. So integrating functions over indefinite integrals. So let's see what this one looks like. In fact, this one is exactly in the pink box up here. So it's good practice to write it out, right? I'm going to zoom in here a little bit. So we are going to say that this is the limit as I'll use b because it's the upper boundary as b approaches infinity from 1 to b of 1 over x dx. And still the limit as b approaches infinity. I know inside of that integral is 1 over x. We all know that's natural log of x by now, between 1 and b. So the limit as b approaches infinity, natural log of b minus the natural log of 1. Natural log of 1 is 0, which is great. So now I have the natural log of infinity. And that's not a real math notation, but that's kind of our working handwriting. So the natural log of infinity, what is that? Well, here's your natural log curve. As x gets larger, so does y. So this is infinity. But we're not going to leave it as infinity anymore. Now we're going to include the word diverges. Gets bigger and bigger and bigger and bigger. So the area underneath that curve, 1 over x, between 1 and infinity, we can't calculate because it keeps going to infinity. So all of this has an area of infinity. All right, let's try the next one, letter B. So same idea. We are going to practice rewriting these in excellent calculus notation. So the limit as a approaches negative infinity of a to 0 of e to the x dx. Now, what are we going to do? We're going to find the antiderivative. So this is the limit as a approaches negative infinity. The antiderivative of e to the x is e to the x between a and 0. So we have e to the 0 minus e to the a. Limit as a approaches negative infinity. E to the 0 we know is 1. E to the negative infinity. So remind yourself what's going on there. This is 1 over e to the infinity. E to the infinity is really, really large, so this is a fraction. This becomes 1 over a really, really big denominator, so this is 1 minus 0, which is equal to 1. Awesome. Okay. And sine. What's going on here? I feel like this one might be a little bit different. Let's do the limit as b approaches infinity of pi over 2 to b sine of x dx. The antiderivative of sine, if we were in class together, you would all shout out that it's cosine. Is it positive or negative? It's going to be negative. So negative cosine of x between pi over 2 and b. This is the limit as b approaches infinity. Negative cosine of b minus negative cosine of pi over 2. Okay, so plus cosine of pi over 2, negative cosine of b. And this is still the limit as b approaches infinity. Cosine of pi over 2, I know that's at the top of the unit circle. Cosine is equal to 1. Negative cosine of b, so negative cosine of infinity. So what happens there is, as we go to infinity, so here's your cosine curve, dude. As you go to infinity, cosine alternates between 1 and negative 1. So while that value doesn't actually go to infinity, it doesn't go to one exact value. I just want to double check the notation. So the textbook says the limit does not exist since as b approaches infinity, the value of b oscillates. They use that word oscillates. Oscillates between negative and 1 and 1. So this integral diverges. So this is a situation where the answer is not infinity, but there is not an exact answer. We don't get a numeric answer. It could be anywhere between 0 and 2. Because if this is plus or minus 1 and anything in between, and I know that I'm adding a 1, as low as I could go would be 0, as high as we could go would be 2, and there's no end. So this one also diverges. Awesome. Example 2, determine whether the integral from negative infinity to infinity of 4x cubed diverges or converges. So what we want to do with this is break it into two pieces. Um, I know it feels like you can just find the antiderivative and throw in the infinities, but if we're using proper official math notation, we're going to break this apart. It would be the limit as a approaches negative infinity of a to 0. We're going to include a pit stop at 0. 4x cubed dx plus the limit as b approaches infinity from 0 to b of 4x cubed dx. Did I have to stop at 0? No, it's a convenient place. You could stop at 1, you could stop at 2. I mean, whatever feels appropriate for the problem, but 0 makes a good middle ground there. So then what we're going to do is integrate each improper integral. So let's start with the one on the left. The limit as a approaches negative infinity, antiderivative of 4x cubed is going to be x to the 4th between a and 0. So this becomes 0 to the 4th minus a to the 4th. And if we put negative infinity in place of the a, negative infinity to the 4th power is a positive infinity. So the result is negative infinity. Right away, I know that it diverges. D-I-V-E-R, diverges. Now, because the first piece diverges, it doesn't matter what happens with the second piece. It could come out to a number 2, but I'm pretty sure you can tell by looking at it, this one will also be infinity. But because one piece of it diverges, the entire thing diverges. So we will say that this diverges. I guess my point is there's no reason to go through and do the second part as well. You can if you want to be super duper thorough, but you don't have to, because once you say it diverges, done, it diverges. All right, let's interpret an improper integral geometrically. So let's see what's going on here. If I have the area under the graph from a to b, this is our regular integral. This is what we've been talking about all along, calculating the area underneath f of x above the x-axis between x equals a and x equals b. It gives us this finite area. With an improper integral, the area under the graph of f to the right of a can exist. It feels like it shouldn't, but it really can exist. And that takes a little bit to wrap your brain around. You can calculate this area, and if it gets small enough fast enough, there is actually a finite area. And I know that's weird. It's going to take some getting used to, and we'll come back to that a little bit. But I think I mentioned something when we did series, and we'll just draw this off to the side. If I have a box that I know is 1 by 1, the area is 1 times 1, which is 1. Cool. I can split this box into 2, and I can say, okay, 1/2 plus, well, I'm going to split it apart again, 1/4. So I'm adding 1/2 plus 1/4. All right, what's 1/2 of that? That's 1/8. Okay, what's 1/2 of that? That's 1/16. Plus, what's 1/2 of that? It's 1/32. Smaller and smaller and smaller and smaller. So you never reach an end. You can keep adding half of a fraction each time. It keeps getting smaller and smaller and smaller. But I haven't changed the area of my box. It's still 1 by 1. So even though you're adding an infinite number of terms, even though you're adding an infinite number of little rectangles out here, if it decreases fast enough, you can still have a finite area. We are going to do more with that later in Unit 10, but just kind of start getting used to that idea right now. So example 3, determine whether the area under the graph of y equals 1 over x squared to the right of x equals 1 is defined. So is it defined? Can you find the limit of that? So here's what we're going to do. We're going to start by setting up the integral. So our integral, we want to be to the right of x equals 1. So here's 1 to infinity of 1 over x squared. Don't forget the dx. And I know with proper math notation, I need to use that limit expression. So this is the limit as, we'll go b. b approaches infinity, 1 to b of 1 over x squared dx. Now, we really want that to be natural log of x squared, but it doesn't work, right? Natural log only works with x to the first power in the denominator. So I know that this is the limit as b approaches infinity, 1 to b of x to the negative 2 dx. So what's the antiderivative of x to the negative 2? The antiderivative of x to the negative 2 is x to the negative 1 divided by negative 1 between 1 and b. We know we substitute those boundaries. And I'm going to put the x back in the bottom at the same time. So I've got negative 1 over b minus a negative 1 over 1. Now, something happens here. So I have a plus 1 in the end. And if I put this infinity in place of this b, 1 over infinity is 0. So 0 plus 1 is 1. Guess what? The area is defined. The area is defined to be 1. And I know that feels weird. I know that feels weird. In fact, it happens so much and it's so common that we have a theorem. And this is a little important right now, but it's really important later. So it's one of these that, again, it's good to just be familiar with, introduce yourself to. Here's my theorem. If I have the integral from 1 to infinity of dx over x to the p, and p is the exponent that's on the x, it will always converge if that exponent is larger than 1. But it will always diverge if that exponent is equal to 1 or smaller. So we'll get really good at these later. But for example, if I go from 1 to x, or excuse me, 1 to infinity of 1 over x squared dx, I know that this will converge. And if I have 1 to infinity for my integral of 1 over x dx, I know that this one diverges without doing any math. This has a special name, or it will have a special name later, and it's a little silly, but it's called the p-test. And we will use that later on in Unit 10 when we talk about whether series converge or diverge. We have a whole unit dedicated to just converge and diverge. All right, so the other type of improper integral. If a function is continuous on a to b, but not defined at a, then the integral from a to b of f of x dx is an improper integral. So what is this really saying? And the other one goes for the other side of it. If the function is not defined, right here, if the function is not defined, you can still find the integral, but you have to introduce a limit. So just like back in the original unit, our first unit together, we could find, we had a graph, there's an open circle where something wasn't defined. We can still find this area up to that open circle, but not including the open circle. And the way that you get around that is by using a limit. So that limit gets us as close as we can to the unit circle without actually hitting, I said unit circle, open circle, without actually hitting that open circle. So determine whether the area under the graph of y equals 1 over the square root of x from 0 to 4 is defined. Now, so what you'd probably do is just set up your integral. You're like, okay, 0 to 4, no problem. 1 over the square root of x dx. Bring this up to the top and go on my way. You have to think about the domain of that original function. And I know domain doesn't get a lot of love. Nobody really likes it. We kind of scooch right over it, myself included. But in this particular problem, it doesn't exist at 0. The function doesn't exist. I'd have a divide by 0 error, which does not work. So we're going to use this with correct math notation. The 4 is fine. That's part of the domain. The bottom is going to be a, but it can't be the limit from both sides. You just want to be on the side of the shaded region. So a from the right, and this is the limit as a from the right approaches infinity. And I think I put my plus sign in the wrong spot. There we go, like this. Okay, so the antiderivative of x to the negative 1/2 is x to the positive 1/2. Divide by positive 1/2 means multiplying by 2 between a and 4. And again, this is the limit as a, and I said infinity. I did it wrong. I made a mistake. What should it be? It should be 0. It should be 0. It's a Friday morning where I was really hoping we'd have a delay and it didn't happen. I'm a little fuzzy. Okay, so let's write the next line a little neater because this is a mess. So the limit as x approaches 0 from the right to square root of x between a, because I know it's not continuous at a, the function's not defined at that a, and 4. There we go. So this will be the limit as x approaches 0 from the right, 2 square root of 4 minus 2 square root of a. This becomes 4 minus 2 times 0. I can substitute the 0 with no issues. So 4 minus 0 is 4. Awesome. So the area is defined. The area is defined. All right. I want to make sure I don't miss anything. Okay. Here we go. Determine whether the integral from 0 to pi over 2 of tangent of x converges or diverges. Remember, converges is a numerical answer. Diverges is does not exist. Maybe that one problem that oscillated, or it goes to infinity. So the reason why this one's an improper integral, we have to think about where tangent is not defined. So think of your unit circle. Tangent of 0 is over here. I know my coordinates are 1, 0. Tangent is y over x, so 0 over 1 is 0. That's no problem. Pi over 2 is up here. The coordinates are 0, 1. Tangent's 1 over 0, which would be infinity, which is undefined. So this time, my problem area is that pi over 2. So when we write this problem, it will be the limit as b from the left, because that's where the shaded area is, approaches pi over 2 of the integral from 0 to b of tangent of x dx. So it's basically like you're removing any of those problem areas and replacing it with the limit to that variable. Now, tangent is not the answer to one of your derivatives on the golden ticket, but it is on the integral side, and it's natural log of secant. So this is the limit as b from the left approaches pi over 2, natural log secant x between 0 and b. So the limit as b approaches pi over 2, b from the left, natural log secant of b minus the natural log secant of 0. All right, secant of 0, secant has to do with cosine. So this is 1 over cosine of 0. Cosine of 0 is 1. So this is the natural log of 1. Go away. Natural log of 1. And secant is, again, related to cosine. Cosine is the x value. So this is natural log. This might be easier to see. 1 over cosine of pi over 2. So cosine of pi over 2, I know is equal to 0. So now I'm finding the natural log of 0. Well, 1 over 0. Let me back up. Cosine of pi over 2 is 0. 1 over 0 is infinity. So this is the natural log of infinity minus the natural log of 1. So natural log of 1, I know, simplifies to 0. Natural log of infinity is still infinity. So we don't leave that as an answer. Now we say that it diverges. Can you tell I'm half asleep? I messed up the plus signs on this problem. Good grief. It should be pi over 2 from the left here. Okay, that looks a little better. Did I do it on the other one? No, just this one. Not sure why. All right. So on example 5, we know that one of those endpoints wasn't defined, so we bring in the limit for the improper integral. Example 6, and I believe this is our last one. Determine whether the integral from 0 to 2 of 1 over x minus 2 quantity squared dx converges or diverges. Just a little throwback here. 1 over x looks like this. 1 over x squared. You take the negative piece that's in the third quadrant and it flips up to the second quadrant, so it looks like this. And then if you have that minus 2, it's going to shift the whole thing to the right too. So you have a vertical asymptote at 2. And if we graph this, well, let's go with a different color, orange. I know that it looks like this. It will definitely pass through this point, it will pass through this point, but it will not cross over the x-axis. You have a horizontal asymptote there. Okay, so we want to know the integral from 0 to 2, and 0 to 2 is this region here. No, it's not. It's on the other side. If you haven't turned the video off yet, congrats. This is not my best one ever. All right, 0 to 2. So the question is, does it get small enough fast enough, even though it looks like we'd have infinite area over here as we get close to 2, does it get small enough fast enough for it to work? So this will be the limit. And the problem area this time is the 2, not the 0. As b approaches 2 from the left of the integral from 0 to 2, 1 over x minus 2 quantity squared dx. All right, technically we probably have a little u substitution in here where u is x minus 2, du is dx. This is going to be the integral of u to the negative 2 if I bring it to the top, so we'll take that whole expression to the negative 1 and divide by negative 1. So if you need a second to do that on the side, that's completely fine. But I'm going to keep going here and keep things in terms of x. So this is between 0 and 2. So now we have the limit as b approaches 2 from the left, negative 1 over 2 minus 2 minus negative 1 of 0 minus 2. All right. I have infinity on the first piece. 2 minus 2 is 0, negative 1 over 0 is infinity. The plus or minus piece doesn't really matter at all here. And this one is plus 1 and a negative 1/2. So if I have infinity and add a negative 1/2, no matter what I do there, the answer is positive or negative infinity. And I know that mattered in the limit unit, but it doesn't matter here. We get to just say that it diverges. I don't have a nice, neat numerical answer, so it diverges. So again, haven't really taught you anything new. We're just taking that idea of antiderivatives and the fundamental theorem of calculus. We're applying some of that limit stuff in infinity that we learned about earlier in the course. So that's it for 6B. We're going to practice over the next couple of days. We'll have an assessment, and then we're moving on to Unit 7. It's a quick class. I am going to look in Delta Math to see if I have improper integrals in there. I believe that I do. So again, you can do the Delta Math practice problems or the book practice problems, but no matter which of those you do, I'd like everybody to try the AP practice problems. There's just something about that AP wording that's different than writing regular test problems. So keep up the great work. I know it's a lot. I know I ask a lot, but you really do a great job. So keep it up.